Intro to Calc. Hope you guys are having a fantastic day. We are moving on to section 3 of chapter 2, which is calculus, a single variable. And we are going to be talking about the derivative function. In the last video, 2.2.1, we talked about like the derivative at a point on a graph. And so now we're going to expand that for any points on any graph. But we will be, in this particular video, we're going to be talking about how to like estimate values of the derivative using a table. We're going to figure out how to kind of graph a function's derivative and then relate a function's graph to the derivative's graph. Exploring the derivative graph graphically, the derivative function graphically is where we're going to start. Okay, so really what you want to do is kind of pick points on the graph that you have, and then use like a straight edge or something, right? If you're good at visualizing the slope of the tangent line, that's cool. So you can like kind of draw little lines. But what you want to do is like estimate the slope of the graph at many points on the graph. Because for most graphs, aside from like lines, the slope changes, right? So like if we're looking at this example, right, graph the derivative function f prime of x of the function f of x below, right? If you notice, like this one, the slope changes at every single point. Like the slope here is different than the slope here, and it's different from the slope here, and it's different from the slope here, and it's different from the slope here. And so what you want to do to like graph the derivative function is you want to pick points on the graph and find the approximate slope at those points. So I think it'll make more sense if we work through one together. So let's look at this graph first. So step one is you pick a few points. Okay, these are the points I picked because I wanted to see kind of like where things change. So I can tell that the slope from like here to here-ish are negative. So I want to see kind of get an approximate slope there, an approximate slope here, because that's kind of where it changes. I kind of picked this point here because it looks like the slope is really close to 0. Here again, the slope is close to 0, but like it's kind of increasing here. So I've got a negative slope, and then I change to a positive slope, and then I have like a 0 slope here, and then a negative slope, and then a 0 slope, and then a positive slope. So basically I wanted to just like pick some points that I thought would be helpful to kind of like pick the turning points. So let's look at this first point here. So what you want to do is you want to draw like a little, oh man, I got low battery. Got to do this quickly. I want to make like a tangent line to the curve that's approximately the same slope as the curve at that point. So this is kind of my estimate for the tangent line at that point. And so what I want to do is look at the slope there. So it looks like, I'm going to say this is about at like halfway through the box. So I would say I go over a half and down, right, and up 2, right? So my slope here should be about rise over run, which is 2 over half. But keep in mind that this slope is going down, so it's actually a negative slope. So I would say the slope's about -2 over a half, which is the same thing as -4. And so what I do is I actually take this point as -4, and that's my y coordinate of my function, my derivative function. So this is at x, here's x is -1, x is -2. When x is -2, I think the derivative is approximately -4. So I actually have a point down at -4. Okay, so then I'm going to repeat that again for this next point. So I draw in my next tangent line. So at x equals -1, This is approximately my tangent line here. Approximately. So I kind of want to find the slope of this line. So I extended it out so that maybe it's easier to see the slope. But what I'm looking at is at -1, I go over 1 to the left to -2, and I go up like probably about 3/4 of the way up. Again, it's still a negative slope, so my rise over run is about -3/4 divided by 1. So that would be my slope at -1. So then I want to put a dot at about -3/4 on the x when x equals -1 for my derivative graph. Then I look at my next point. So this one I picked because it looks like the slope is about 0. So my tangent line is about a horizontal line, right, where the slope is 0. So I wanted to do that because I want to know where it crosses the x-axis. It's just helpful information to know. So then my next point here would be the slope of the graph at that point, which is 0. So I'm going to put a dot right here at y equals 0. So next you kind of want to figure out like what happens between this point, this blue point here that's kind of hidden now, and this blue point here, because this is another spot where the derivative is about 0. So I can put another 0 point there on the graph, but it's important to look at the function, which is kind of covered up at this point. So I'm going to just kind of erase my axes for a second. But notice that like the graph kind of starts to slope up a little bit. So I should actually have like a positive slope, a very small positive slope in between this 0 slope and this 0 slope. So I'm just going to put a positive dot there because my slope in between here and here is positive. Okay, it's increasing. So then I go on to my next point, and you keep going. So I think at this point you have enough information to like try the rest of it on your own. I'm going to go ahead and fill in the rest of the graph, and you see if you can do it as well. Okay, so after looking at the tangent lines or the slope of the tangent lines along the curve, what I found is that here it's around a slope of -1. This is about a slope of -0.5. This is a slope of 0. And this is a slope of around +2. So what I did is I just plotted points at the slopes. So here, -1, here's -1.5, here's 0, and then here's the +2. So then we just kind of like connect the dots smoothly and create my derivative graph. And there you have your approximate derivative graph. Compared to the original function. And the thing that's nice about this is like if you have the derivative graph, you can tell where the original graph is increasing and decreasing and where the slopes are 0. So wherever it crosses the x-axis, that's where the slopes were 0. Anytime it's above the x-axis, that means the slope was positive. Below the x-axis, the slope is negative. Here again, you have, below the x-axis, the slope is negative, which is true about the original graph. So that's kind of how you would generally do the graph. So let's label it appropriately. So I'm going to call my original function f of x. That's the blue. So I'm going to call this f of x, which means my derivative function is f prime of x, right? Because that's our notation for a derivative. The other notation, I forget if I taught you the other notation, but it's just dy dx. And in this case, df of x over dx. But this we'll probably use more often. Okay, let's go back up for a second. So the question here asks, how do you know if a function is increasing or decreasing on an interval? And we already kind of talked about this. So if you have an increasing function, right, that would be like this little spot here and this spot here, right, where it's going up. is if the derivative is positive. So in this case, right, I know that the derivative is positive here because it's above the x-axis, and I also know that it's increasing here. It's above the x-axis as well. So we know if a function is increasing or decreasing, or if a function is increasing on an interval a to b, if f prime of x is positive or greater than 0 on that interval. And the opposite is true for decreasing. F prime has to be less than 0. Okay, so there you go. You also know if f prime equals 0, you know that the function either has a maximum, right, because it has to go like this, or a minimum because it goes like this, or something where, like on y equals x cubed, where it changes from, not where it changes from increasing to decreasing, but it's just it kind of flattens out, right, and you end up with a slope of 0 here, and then it comes back down. That you would also know, right, when f prime of x equals 0, like that's also really helpful information as well. So now we have a couple examples. I'm going to zoom out so you can see. No, that's a really bad idea. Okay, sorry. Okay, I'm going to just show you one example at a time. Okay, so try example 2 and example 3 on your own first. And then I will go over them. I have about 4 minutes left in the video, so I'm probably going to go pretty quickly. And I'll probably do most of the work with the screen paused, but then I'll explain how I got what my answer is. But I think it's really good for you to try these examples on your own. Make sure you understand them. Okay, this is just one example for number 2. You could have had something very different from this, but all this means, right, is that f prime is greater than 0 for x is less than -1. So any values less than -1 on the x-axis, so from here to the left, has to be an increasing function. So that's why I drew mine increasing like this. At -1, I have a 0 slope, which means in this case it's a maximum. And so my function levels off, and then it turns back around and now has a decreasing slope, which is the second bullet here, that f prime has to be less than 0 when x is greater than -1. So anything to the right of -1 has to be decreasing. Okay, example 3, for what value of x does g prime appear to be closest to 3? So in this case, you might want to look at the average slope between each of the 2 points. So 4.4 minus 3.4 divided by 3.2 over 2.7, or minus 2.7, and kind of do this for every single set, and then you want to find the derivative that's closest to 3. Remember, derivative is just the slope at that on that interval, or at that point. And so your average or your estimate for the derivative is just going to be your y2 minus y1 over x2 minus x1. Okay, so for example 3, I just calculated the average slope between each of the 2 points. So here I got it to be 2, then 1.2, then 0.18. Then it increases again to 1.2, 2.8, 3.2 to 4. And so the question is asking for what value of x does g prime appear to be closest to 3? Well, you notice that here, so from 6.0 to 7.4, the slope is about 2.8, and then here it's 3.2. So both of those are the same distance away from 3. So I would guess that the x value of 5.2 approximately has a slope close to 3. Okay, so then try example 4 on your own. That's the last example. It says in the graph of f in figure 2.3, 2.31, at which of the labeled x values is, okay, answer the questions. Okay, go ahead, try them. So for A, I'm looking for the greatest value of the function. So that's going to be the highest y value, and that is at x3. So I just like I made little horizontal lines to find the y value just to compare the y values at the different points. F of x is the least at x4, so that's down here. And then for C and D, you're looking at the slopes. The largest slope is at x1, and the smallest slope is at x3, where it's negative. Yay!